This video is about the cardiac dipole. It corresponds to the second part of section 41.3 of the Applied Analog Electronics textbook. The cardiac dipole is what we're actually measuring with the EKG. And let's take a look at what I mean by the dipole and where it comes from. Now, if you can remember from when we talked about action potentials, when we're looking at the tissue outside the muscle cells, there is an excess of Na+. That is an excess relative to what's inside the cell that gives this a positive potential relative to the inside of a cell. And we can't really measure that potential because we don't have any electrode inside the cell to make the voltage difference. But when the cell depolarizes, we get less sodium outside the cell. Sodium goes into the cells. And so if we've got a region where depolarization has happened, there's less positive charge outside the cell than in a region where the depolarization hasn't happened yet. Now, if the whole heart depolarized all at once and the thing just went boom, then there wouldn't be much signal for us to look at. But the heart doesn't all depolarize at once. The depolarization travels through the cells. Basically, when one cell depolarizes, then the one after it does, and the depolarization travels as a wave through the muscle tissue. And that means we've got sort of a wave front here, and it's, say, moving in that direction, because this is the part that hasn't depolarized yet, and this is the part that has depolarized. So we have depolarization wave traveling that way. Now notice that on one side we've got more positive charge than on the other side in the external tissue here. And that difference in charge means we've got a voltage difference between those two sides of the wavefront. And so we've got positive on this side and negative on this side. If we put electrodes out here on the body somewhere, we'll be able to see that voltage difference across the wavefront. And so if the wave is moving towards one of our electrodes, so if this is our VP electrode out here, and the wave is moving towards it, we will see a positive voltage as that waveform moves, as the wavefront moves, assuming that the negative electrode is out here somewhere. If the waveform is moving in the opposite direction, then the positive side would be in the other thing, and we'd see a negative voltage on this electrode. So the basic idea here is that what the electrodes are detecting is not depolarization itself, but the movement of the depolarization wave that gives a region that is depolarized and a region that's not, resulting in this electric dipole. And that's the cardiac dipole. When the cardiac dipole, resulting from the motion of the wave, basically the cardiac dipole points in the direction of the motion of the wave. And so you can track the motion of depolarization waves through the heart by looking at, simultaneously over many channels usually, the different electrical field around the heart. It's kind of hard to see that here in this simple one-dimensional view where just a single line is moving across the paper. Let's take a look at a view where we've got something that looks more like the ventricles of the heart. Okay, so this cartoon, which is from Natalie's casebook, there's a full citation in the book, is showing the depolarization wave that happens when the ventricles contract. So when you get the big squeeze that pushes the blood out through the circulatory system. And what you can see is that that center part there, the septum that separates the left and right ventricles, is where the depolarization wave starts. It travels down the septum and out to the outer part of the heart. And the arrow, the black arrow here, is pointing in the direction of the cardiac vector. And you can see it's not always pointing in the same direction. This is only showing a 2D view, sort of a vertical slice through the heart. It's actually moving in 3 dimensions because the heart is a 3-dimensional object, not a 2-dimensional one. But you can see that where the arrow there is the largest, where you get the strongest vector, it's kind of pointing along the septum. And if we go back to looking at what the sort of canonical EKG waveform looks like, remember there's a little part here, and then it goes way up, and then another part here. The first bump here is P, then we have the QRS complex, and then another bump T. The P is the atrial depolarization. And that wasn't shown in the cartoon. The cartoon there was just showing the ventricles. The QRS complex is the ventricle depolarization. And the R, that big spike, is the cardiac vector along the septum there, where it was both large and pointing in the same direction for a while. And the reason we get this as a positive spike is that the septum basically points down and to the left in most people. And so if you're looking at it on lead 1, which is left arm minus right arm, the cardiac vector it's pointing towards that, so well, maybe 45 degrees off from that, but it's still pointing from right to left. If you look at lead 2 is left leg minus right arm. Now that's almost straight along the septum for most people. And so lead 2 usually gives you a very clean signal, like the PQRST signal we see here. But wait a minute, where'd that T come from? I only explained P being something to do with the atrium and QRS being the ventricle depolarization. T is the repolarization. Now the repolarization wave is going from less Na plus in front of the repolarization to more Na plus behind the repolarization. So you would expect that if a repolarization wave is moving towards an electrode, you'd get a negative spike. And indeed that's correct. But we're getting a positive spike here. This doesn't make much sense. If the depolarization wave is following behind the repolarization wave, then we should get a negative spike. Well, let's go back to looking at cartoons of the heart. And again, we'll look at Natalie's casebook, but now instead of looking at this depolarization, let's look at sort of the full cycle here. Depolarizing, the one we saw animated. Depolarized when basically everything is being squeezed because the calcium is still there, causing the contraction of the muscle cells. And then the repolarization is as the muscle cells relax again. The thing is that the outer cells and the inner cells of the heart don't have the same time constants for the repolarizing. The outer cells of the heart repolarize faster. And so the wave for repolarizing starts at the outside part of the heart and works its way inward, the opposite direction from the depolarization wave. So because the wave is traveling in the opposite direction, the cardiac vector is in the same direction that it was before because the repolarizing has got the minus and plus. Basically, if you look at the left-hand side and the right-hand side of this image, you basically see the same configuration of charge with the positive on the outside and the negative on the inside. And so the repolarization wave basically gives the same sort of signal that the depolarizing wave does. Now, there are some differences. If we go back to looking at that waveform, the T wave here is much smaller and broader than the R spike. And that's because the repolarization happens more gradually. The depolarizing is very fast, very abrupt, because that sodium rushes into the cell really fast. That happens in milliseconds. The repolarizing is slower and more spread out. So the repolarization wave moves more slowly, and it basically just takes longer for that to happen. So you get a lower longer spike for the T wave, for the T part of the wave than for the P, than for the R. Sorry, P is the atrial depolarization, which we've not talked about at all. Now, because what we're looking at with an EKG is the movement of these depolarization and repolarization waves through the heart, a trained cardiologist can get a lot of information from those EKG signals. Subtle changes in the timing, subtle changes in the direction of the cardiac vector can indicate scar tissue or other sorts of damage to the heart. And there's lots and lots of different sorts of damage to the heart that causes different subtle changes to the signal. And cardiologists spend years learning how to interpret EKGs. We're not going to do that. For purposes of this course, it's enough to have the sort of vague understanding that, okay, the P wave is the atrial depolarization, the R spike is the ventricle depolarization, or actually the whole QRS complex is, and the T is the repolarization. That's probably about all you'll be able to see in this sort of crude one-channel EKG you'll be doing, but it's enough to get a fair interpretation of whether or not your heart's beating, how fast it's beating, and basic shape of which way the depolarization wave is moving in your heart. And that's enough for this course. So I think that's enough for this video also.